So we pick up the topic today, exponential generating functions and the law of large numbers. But I'd first make a video on the exponential generating function. So on moment generating function. So big topic is moment generating functions. We have seen them pop up in the lecture, but now let's do this right. Before we get started with moment generating functions, we look at one particular generating function. So let's do that first. And the one we look at is the exponential statement. Exponential generating function. So you start again with the sequence of a 0, a 1, goes on up to infinity if you want. And this sequence defines a function. Now we call that function, before the function was called g, but now we take a capital E. And then we define that function as the infinite sum from n is 0 up to infinity of the an, and now times t to the power n divided by n squared. And maybe you have seen this function before. So if you set a1 equal to a2, etc., if you set them all equal to 1, then you get the series t to the n divided by n factorial, and starts in 0 up to infinity. And you might actually know that this is a Taylor series for the exponential function. And because that's the exponential function, if you set all the a's to 1, we still call this an exponential generating function. So now, moment generating functions. So now we combine generating functions with random variables. So we take a random variable x, and you remember what the moments of the random variable are. The moments are the expectation of x, x squared, and in general x to the power k. If x is a discrete random variable, then I know how to write down my expectation, right? So it's the sum of the possible outcomes to the power k times their probability. And this is all outcomes I have sometimes. All I. And now we define the moment generating function. We define this as expectation of e to the t times x. So this is just to say this is something different than that one. So this is the expected value of the random variable x taken as exponent, t times x as exponent. So now we combine these things. So take our exponential generating function, and now we just choose something particular for the AK or AN. We choose AN equal to the moment number n, or AK equal to the case moment. So what happens? You can still write down t, well, that is the sum, and now we have to replace the AN by what we have defined them to be, so it's these expectations. And it's still t to the n divided by n factorial. And now we can use the additivity of the expectation. So this is the sum and this is an expectation symbol. So essentially we can take the elements of the sum and write, well, let's script, they're actually friendly. And the first thing they say how the sum looks like. So if n is equal to 0, then x to the power 0, that's just 1. And then it's t to the power 0 divided by n factorial, that's also 1. So for n is 1, I just get a 1. And then if t is 1, then I get the first moment, x, and t to the 1 factorial. And the next element will be the second moment, multiplication of x squared, and t squared divided by 2 factorial. And it goes on. And now this is the sum of expectations. So let's write this as an expectation of sums. It's the expectation of 1 plus x times t. Okay, write it nice as t times x divided by 1 factorial plus t squared x squared 2 factorial plus, let me give here, t x to the power 3 factorial. Goes on, dot, closing brackets of the expectation. We recognize what this is. This is the series, but with t replaced by tx. So if I take here tx to the power of n, then I get also a tx e to the tx. And I can finish the calculation here. I get the expectation of e to the t times x. So e for that particular choice of sequence numbers gives me the moment generating function. And let's add here on that board. Can you see this? Yes, you can see this. So we call that m subscript x if we want to make clear which is the right, which is the random variable x, which this belongs to, and then a function of t. So you're computing the expectation for different values of t. Maybe t is equal to 0, or t is equal to 1/2, etc. And then you get a function where you can vary the t. And here, this one is equal to m of x by the calculation we have done. So So we have defined the moment generating function. And we remember from the previous board that you get the moment generating function from the exponential generating function by setting the an equal to the moments. And that now let's continue. So think of our moment generating function. So it's a function of t, and one thing we can do is we can do Taylor or Maclaurin expansion and write this function as a series. It's an infinite sum from n going to 0 to infinity of the derivatives of the function. So I'm taking function mxt, and then I divide by n factorial and t to the power n. And here I have the nth derivative. So if n is 0, I have the function itself. If n is 1, I have the first derivative, and so on. And the result about the exponential function that you can write it as a series is a special case of that. So, but wait. Now we have written mx as a sequence, as a series with certain coefficients. But we also said that it is a series with certain coefficients. It's the exponential generating function with the coefficients an is equal to the moments. So that means that what's ever written here, that's our an. So before we have written them as e to the xn. Now Tn divided by n squared, n factorial. So that's very nice. If this is the same than that for every t, that must mean that I can get my first moment as first derivative of the t of the mx function in 0, because a small correction, you expand the series, so you expand the function of t by looking at the derivatives in one particular point, which I choose to be the point 0. And then I have this. Okay. So we have the first moment is the first derivative, and in general, we have that nth moment I can obtain as derivative, the nth derivative of my moment generating function. Sometimes I leave the x there, evaluated at 0. So as a function, you take the entire derivative, and then you look at the value in some particular point 0, and that gives you the moment. And well, that's a good reason to call this a moment generating function. So let's continue and do an example. Examples are always good. So let's do the binomial distribution. So what's my binomial distribution? You remember it's the distribution with the density function. Let's use the exact same notation as the script. It's fk is equal n over k. So how many ways I can take k objects out of a bag with n objects. P, the probability parameter of the binomial distribution. X, which is binomial distributed with parameters n and p. And then they have this density. P to the power k, 1 minus p to the power n minus k. So if you have k successes, then you have to be k times luck. Each time you have luck with probability p, and n minus k times you have no luck, 1 minus p to the power n minus k. But then you can still choose the order in which you have luck and have no luck. So that's counting the number of possible ways you can choose. So what's the moment generating function of what is the expectation of e to the tx? So you remember this is a transformation. I think that might be the theorem of the heart. So I'm applying the function h, which is h of x, which is equal to t times e to the tx. Let's remove it and just do the step. So we get the sum over, now before we had the possible states, but now we get the function et k, where k are the possible states. So we apply our function h to the possible states. And then we still have to multiply with the probability to get that state. And we have argued of this form for binomial distribution. Coming from at least 0 and at most n successes. So this is, you could write this maybe a bit more suggestive as e to the power t to the power k, just using the rules of the exponent. And then you can see that you have here something to the power k times something to the power k. So we can rewrite this as still the same summation. N over k et times p to the power k, 1 minus p n minus k. But that is sum up to n. But this is a formula where we know the result by the binomial theorem. So we can write this as, we can summate this and write this as e to the t times p plus 1 minus p to the power n. If you would write this as this term times the same term, and then multiply everything out, so you can choose this one from this sum, and you see that at the end you get this summation. Then I'm just doing the step backwards. So if you want to check this out, then look for the binomial theorem. So what do we have? We started writing down the moment generating function, and we have actually computed it here. So that is my moment generating function. It depends, of course, on the parameters n and p of the binomial distribution. The random variable x has that distribution, and then it contains a dependence on the free parameter of the function. So m x of t, we vary t, and we're looking at this object for different values. And so one thing we can do now is compute moments of the binomial random variable. So we can compute, for example, e of x, the expectation. And then that will be so let's first take the derivatives, maybe that's easier. So let's write m prime xt. So I'm taking the derivative as a function of t. It's e to the t p plus 1 minus p to the power n. So if I want to take a derivative, then I have to take the outer derivative n times e to the t p plus 1 minus p now to the power n minus 1. And then in the next step, we have to multiply with the derivative of the inner term. So this part does not depend on t, that disappears. And this part is e to the t times something, and the derivative of e to the d is e to the t. So we multiply with e to the t times p. So this is the first derivative. And if you want to actually have a moment, then you compute the derivative. The first derivative is evaluated in 0. So we are plugging in 0, that is n times 1 times p. But something magic happens. P plus 1 minus p, that's just a fancy way of writing 1 and 1 to the power n minus 1 is still 1. So 1 times 1 times 1 times 1 is 1. And everything is equal to np. And we have computed the first moment of my random variable x. So we could now go to our table of the binomial distribution and write down bin n k in the column for the moment. This moment of expectation, it's n times p. So this way we can start to fill up the table and do this for different distribution and find the first and the second moment. So let me clean the board and come back. Let's compute one more moment, the second one, just to get used to doing that. So second derivative. Okay, second derivative. Well, I start with the first derivative and I take once more derivative. So I had the n, but now I also get the n minus 1 as a factor because currently I'm to the power n minus 1. And then what's inside the bracket. And I take the inner derivative, and the inner derivative is still e to the power tb, so I get a power of 2. Right, 2 times the product of the inner derivatives. but that is the derivative. I have the dependence here on t. Let's look at this. I have taken the derivative and I have the dependence here on t, but I also have a dependence here on t, so I have to use the product rule and now take the derivative of everything. Now looking at this t, and one that is easy. And to the t p plus 1 minus p to the power still n minus 1. And now I take the derivative of that thing, so the rule f prime g plus g prime f, and the derivative of this part is just the function itself. So we have also computed the second derivative, and if you want to know the second moment, what we do, this one is just a copy of the first moment, right? So if you plug in m prime, if you plug in t is equal to 0, then here we can already see that this is and b, remember that. And here, on that part, it's n minus 1. Now we're plugging again, the t is 0 in there, and then we get a fancy way of writing 1 to the power of n minus 2. Now it's still 1. And here we get e to the 0 to the power 2. So second moment is n times n minus 1 times p to the power 2 plus np. And now the second moment is maybe not the most natural thing to look at. We're most of the time interested in the variance. But we know the variance is equal to the second moment, second derivative, minus the first moment squared, or the first derivative squared, and then it's equal to n times n minus 1 times p squared plus np minus n p squared. That simplifies a bit. So if you just compute what this is n times p squared times minus 1. So if you just compute what it is, then you get n times p minus n times p squared, and this is p times p squared, so this is equal to n times p 1 minus p. And we know that this is our variance, so we can add to our table the variance of our distribution, and it was n times p times 1 minus p. Display those boards for a moment. Still finish to look at it. Okay. So bit more material on moment generating functions, I have the first thing which could help us, a theorem about moment generating functions. And the theorem is as follows. So I assume that I have two random variables, x and y, and they are two random variables. And they come with their own moment generating function. So I get a moment generating function of x, a function of t. And now it's good that I have these subscripts with the letter. So I get two different ones. And now I have a theorem. And first, it doesn't sound like very useful because it says if these two moment generating functions, if they are the same for all t, then if they're the same for t, then x and y have the same distribution. So that why is this a useful theorem? Well, apparently it's useful because sometimes you can show that the moment generating functions are the same, but it's quite difficult to see that the random variables have the same distribution. So you can get something you want to know from a simpler condition you can check. So this is a useful theorem. And it says x and y have the same distribution. It doesn't say that x and y is the same random variable. And just to give you an example, if you have a random variable, which is nully, with parameter 1/2, that's a coin. So it's 0 with probability 1/2 and 1 with probability 1/2. And if I define y as 1 minus x, so if x is 0, then y is 1, and if x is 1, then y is 0, then y is also the nully. So clearly x and y have the same moment generating functions, and they have the same distribution, but they are absolutely not the same, because every time x is 1, then y is 0, and every time x is 0, then y is 1. So you really need to have the same distribution and not just are the same. Oh, this part is important of the theorem. So one more theorem. Great wisdom, it is called Theorem 2. Second useful result about random variables. So we start with a random variable. And x has, let's start to use the operation moment generating function, and x of t. And the statement is, let's define a y as a linear transformation. Here it's written alpha plus beta times x. So y is a scaled and shifted version of x, and alpha and beta are just two numbers. Then if I change x from y, then also the moment generating function changes. And in fact, the moment generating function for y is equal to e to the alpha t times m, the original moment generating function, and now evaluate it in beta t. So if I change the scaling, I change the t. If I shift then I'm getting an additional factor of e to the alpha t in front of my moment generating function. So now we have two nice theorems, so let's use them for something meaningful, just to illustrate that these are helpful theorems. So let's use them to prove the problem. Prove that x is normally distributed with some mean mu and some standard deviation sigma. Then you remember that if you center and subtract the mean and you divide by sigma, then you get something which is standard, normally distributed. 0, 1. And maybe you remember that I motivated this when I said that you have all the expectation of x minus mu divided by sigma is the expectation of x minus mu divided by sigma. And now these two terms, they cancel each other, and it's 0. And likewise, I have argued that the variance of x minus mu divided by sigma is the variance of 1 minus sigma squared, because I can take the sigma out, and then the variance of x plus the variance of mu. But the variance of mu is 0, the variance of x is sigma squared. So I get variance 1. So I have shown that this expression has the right mean and the right variance to be normally distributed with mean 0 and variance 1, but I also would like to show that it is normally distributed and not some from another distribution with mean 0 and variance 1. So we show that a little bit now. My moment generating function of a normal distribution, so x, you might remember this, that's the example we looked at, is e to the mu t sigma squared times t squared divided by 2. And now y u of z is a linear transformation of x and mu. So what is my beta? My beta I multiply with 1 over sigma. And what is my alpha? Well, I'm subtracting mu divided by sigma. It's mu divided by sigma. Now I'm using the rule that I get the original moment generating function times that factor times that scale. So now that m x minus mu divided by sigma, the moment generating function of that expression, that is equal to e to the minus mu divided by sigma. So that's still there, yes. So this is this part times t. And then the moment generating function of x, but evaluated in 1 over sigma times t. We have written it here, what it is. So I can just expand this. E to the minus mu sigma t times e to the mu 1 over sigma t plus sigma squared, not g, but 1 over sigma t squared divided by 2. Okay, so this one and this one, they cancel. And this is sigma squared divided by 1 over sigma squared. So it's e to the t squared divided by 2. Aha, that is the moment generating function of a standard normal random variable. If you take this one, and you take mu 0 and sigma is 1, and you get that one. So we have shown that our moment generating function of the construction we're interested in has the moment generating function of a standard normal random variable, but then by our theorem, if they have the same moment generating function, they are actually the same. And we can conclude that conclusion, where should I write this? Very small, just conclusion, z is normally distributed mean 0. Very small. Very nice. So last bit on moment generating functions. So what I want to show, the third theorem. So I take x, x1 here and x2, and I say they are independent random variables. And they have moment generating functions, well, and x1 and x2. The result is if you form a new random variable, which is the sum of x1 and x2, then the moment generating function of y is as follows. M of y t is equal to moment generating function of x1 times the moment generating function of x2. Why is that nice? Adding random variables is difficult, and multiplying functions is easy. Adding the random outcomes of random variables is easy, but telling what the distribution is of the sum of random variables, that's difficult. So we had some, for example, said at some point that the sum of two normal random variables is normal again, but we have never really shown it, and it's not easy to show. And in fact, we are going to show it, and the trick we are using is exactly the theorem. So I'm cleaning the board. So my theorem now is much more space efficient. If x and 1 and x2 are independent random variables, then the moment generating function of the sum is the product of moment generating functions. The sum is the product There you can see the exponent in the exponential function and the moment generating function is working. So from theorem 3, we can, for example, show the following. I take x1, I take it normal with mean mu1 and standard deviation sigma 1. And accordingly, x2 normal is mean 2 and standard deviation 2. And now I form x1 plus x2, and I have told you that this will be then normally distributed with the sum of the means and the sum of the variances. I didn't tell you why this is the case, and you can guess we are showing it using the moment generating function. So what do we have to do? We want to show that this has that distribution, so let's compute the moment generating function of that thing. It's the moment generating functions of the ingredients. So product and we know each of these things, so it's e to the mu 1t plus sigma 1 squared t squared divided by 2, and then e to the mu 2t plus sigma 2 squared t squared divided by 2. Now I can put them as exponent of a single e to the power, something to the power. And simplify it a bit. So this is e to the, I can add these two mu's, I get mu1 plus mu2 times t, and I can add these two terms, and then I get sigma squared 1 plus sigma squared 2 times t squared over 2. But yeah, that's the moment generating function of and mu1 plus mu2 sigma 2 1 squared sigma 2 squared, and we have said that two distributions, two random variables have the same distributions if their moment generating function are the same. So in other words, the distribution of that has to be this. So let's do a second example, and that is the case where x1 is Poisson distributed with parameter lambda 1, and x2 is Poisson distributed with parameter lambda 2. And the question is, what's the distribution of x1 plus x2? So the way to do it is writing down the moment generating function of x1 plus x2 t, that is the moment generating function of x1 t times the moment generating function of x2 t. So x1 and x2 are independent, otherwise I cannot do this. And so I compute what it is and try to identify it. And if I want to compute the moment generating product of the moment generating function, the first thing I need is the moment generating function of x1 and the one of x2. So I could just write xi and save a bit of space. And the moment generating function of a Poisson distributed random variable is e to the lambda I, and then e to the t minus 1. So this holds for x1 and x2 with lambda 1 and lambda 2. So then e to the lambda 1 e t minus 1 lambda 2 e t minus 1. You bring it into sum, and then you can just add up the lambdas, lambda 1 plus lambda 2, and then times e to the t minus 1. But then I recognize that is the g f of Poisson lambda 1 plus lambda 2. So I have found my distribution of x1 plus x2, and it's Poisson with the sum of lambdas. Highlights of what we are doing, at least mathematically, that is the most exciting result which can show, and that's the law of large numbers. Law of large numbers, L of n. And we want to prove this. And the tool is Chebyshev's inequality. And Chebyshev's inequality is useful in itself. So what does it say? You start with the random variable x. This mean e effect is mu, just the name of the mean, let's say. And now for any number epsilon larger than 0 you can choose, you have that p of x minus mu, that is in absolute values, that is the distance between the mean and the outcome of your random variable. This is your mean, and this is your random variable. Lands here or lands there. And you're interested in the distance between those. That's this one. And it's best that the probability that this distance is large, so in some sense larger than epsilon, where epsilon you choose yourself, the probability that this is large, so you choose some epsilon, this is mu minus epsilon, and this is mu plus epsilon, and then I have the color. Probability that my x lands either in this area or in that area. So in other words, yeah, the probability that my x is epsilon far away from the mean, I can say that this is not too large. It's smaller than the variance of x, so that's not so small, divided by epsilon squared. So if the variance is large, then my values distribute over larger areas. I expect that if you want to control this, then you get a bound which depends on the variance. And then if you make the epsilon smaller, then the probability will it will get larger that I'm outside. So if my epsilon very close to mu, then actually my probability that I'm in the area outside might be almost 1. And there you see something, this epsilon, if the epsilon gets small, then 1 over epsilon squared can be very large. So if you have epsilon is equal to 0.1, then 1 over epsilon squared is equal to 10. No, 100 squared. So at some point, when you choose the epsilon to small, this bound becomes useless because it essentially says that the probability is smaller than a number larger than 1. But or if the epsilon is reasonably large, then this is a useful bound and tells you what's the probability to have an outlier under that distribution. So time for the proof. So let's follow the script. The script says let's prove this, but let's make our life a bit easier and just prove it for discrete random variables. But the other case of continuous random variables is a bit similar. So fx is the density function of my random variable x, the probability mass function. You want to be careful. And then you have your picture. Here is the mu. Here is plus minus epsilon. And now I'm looking at all possible outcomes. Which are in my bad area, so which are outside my interval. And then I can write down that the probability of x minus mu larger than epsilon, well, that always happens if I'm in my bad region. So if I have an x out of the range, x or these bad x's, not all x's, only the bad outcomes, times the probability to get that x. So also some good ones. So I'm only summing over the bad ones. And now, on the other hand, the variance of x is equal to, well, we just what the variance is defined to be, you sum over all x, and then it's x minus mu squared times f of x. So let's give this a name. Set A is the set of outliers, the possible values which are outside the interval. And then you have, this is x element A, summing over the x's which are in A. And now we have the following argument. If x is an outlier, well, that means that it actually happens that x minus mu is larger than epsilon. That's exactly how we thought about it. And this means that you can also write x squared is larger than epsilon squared. Preserve the inequality. So I can write that my sum is, so I can write that my sum over all x element, so only over that x of x minus mu squared fx, that is certainly smaller because I'm adding up positive numbers over a smaller set than the same thing over all the same thing over all x. But that one is larger than epsilon squared. So I can say that sum of x element A, and now this is even smaller, epsilon squared f of x is smaller than sum over all the bad ones x minus mu squared f of x is even smaller than sum over all x minus mu squared times the probability to get that x. This is smaller than that, is smaller than that. And this is my variance. So what is this? This is epsilon times a sum over probability density, but not over all values. The right direction, what I'm no, not the right direction. This is you put okay, I know how to think about this. You can write this as an expectation, right? This is just a function h, which is epsilon squared if you're in A and it is 0 otherwise. So essentially what I'm getting is the sum of x element A times probability that I'm getting those x is smaller than the variance, and I've divided both sides by epsilon squared. So I have now shown this expression, and this is adding up the probabilities to get the x's which are in the A. So the probability of those x's which are in A, that are the x's for which the distance to the mean is larger than epsilon, and now we finally have it, is smaller than the, is this still on board? Yes, so I can just go down here. That is satisfying that we can draw this box now. And if you want to do the same game with continuous random variables, then you have to replace all the sums by, you have to replace it by integrals, but you still get the same arguments. The moment where I was the most struggling, maybe if I had to think about it for a second, then you also have to think about it. So if I want to know the probability that x is in set A for a discrete random variable, then this is just a sum of the probability that I get outcomes which corresponds to the elements of A. So now we can prove the law of large numbers and formulate it. And now I have an example first. An example for an example for Chebyshev's inequality. It's a simple example. So I'm just using Chebyshev's inequality with epsilon being equal to k times sigma. So maybe 5 times sigma, or 10 times sigma, or 1 times sigma. And then Chebyshev's inequality tells me the probability that my random variable is more than k times sigma away from mu, so the probability that my distance to mu is larger than k times the standard deviation. Well, that is, I have just to replace, it's the variance of sigma, the variance of x, that's sigma squared, divided by epsilon squared, and epsilon was sigma times k squared. So I get 1 over k squared. And you can use this, for example, it means that if k is equal to 2, then the probability that I'm 2 times the standard deviation away from the mean is smaller than 1 over 4. So, in other words, (57% of the values of a random variable with 50% with more than 50% probability, my values are within 2 standard deviations away from the mean. So if I draw my picture, here's my mu, and this is mu minus 2 sigma, and this is mu plus 2 sigma. Then the probability that I'm in here is larger than 75%. And the probability that I'm outside is 12% and 12.5%. So you could use this to compute a p-value, at least estimate a p-value. P-value means that you're in the tail. So what's the probability that a random variable is more than 2 sigmas away from the mean? Well, you can, for some random variables, we could compute it, but in general, you could use Chebyshev's inequality, and then it gives you a nice result. So this maybe for the book, sigma squared here was the variance of x. Okay. So last bit for today and the highlight. So law of large numbers, how? What does it say? We start with random variables. X1 up to and the independent random variables. So next is expected value of xi is equal to mu, and variance of xi, call it sigma square. We need that this is finite. So there are random variables which spread so far over the place that the variance is infinite. And we're saying that's not, then it doesn't work. We need independent random variables where the variance is finite and equal to some number sigma squared. And mean is equal to some number mu. And then we define the sum n, which is just the sum of all my x's, x1 plus x2 up to xn. And the theorem says the probability that my sum divided by n, that's a fancy way to write the average. So the probability that my average value of x from x1 to xn, that this is far away from the mean, so that this is larger than epsilon, this probability goes to 0. So in other words, my averages will be closer and closer to mu, at least with high probability. So I can take a very small, I can take a very small epsilon around my mean mu. So this is mu minus epsilon, mu minus epsilon. And then it says that even if the epsilon is small, the probability that my x bar n, or my Sn divided by n, that this is somewhere outside my interval, that is for large enough n negligible, and for n going to infinity it becomes 0. So this is the law of large numbers, which tells me that sample averages converges to the mean. So what did I say? I just said this means that as n goes to infinity, Sn divided by n comes close. The true mean, the sample mean, comes close to the true expectation. And we have used that before to estimate the true expectation from the sample mean. If you didn't know it, so then this is an instance where we use the law of large numbers. So let's prove this. Let's compute. Essentially, you want to use Chebyshev's inequality. You can already see this. This is exactly of the form which we have a result for. So what do we need? We need the result. We need the variance of the sample mean. The variance of Sn divided by n is 1 over n squared. The variance of Sn is 1 over n squared. The variance of, and now it's summing up the ingredients, and they just sum up nicely because I'm independent. The variance of x1, the variance of x2, up to the variance of xn. So I get sigma squared n times, and that is sigma squared divided by n. Yeah, you know this. It's just restating that standard error, the standard deviation, is sigma divided by square root of n. Tricked you into checking this once more. And what is the expectation of? Well, let's go past the expectation of the sample average is the true mean, and you can show it in the same way. Now I have the standard error on the mean. And now let's use Chebyshev's inequality. It says the probability that Sn divided by n minus mu, the probability that this is larger than epsilon, well, it must be smaller than the variance sigma squared divided by n divided by epsilon squared. Even if you take an epsilon which is very small, then this expression will be large perhaps because you're dividing by epsilon squared. But if you choose a large enough n, for example, n larger than epsilon, n larger than epsilon squared, then this as n goes to infinity converges to 0. And we have proven the law of large numbers. Thank you.